Hello viewers, welcome back to this channel. So in this video, I'm going to be handling the third part under transition chemistry. This video is presented to you by Ogembe Yusuf, and your advice share the video to your friends and subscribe to the channel so that you can all benefit as a family. Now proceeding with the third video. The first video that we made about transition chemistry was dealing about with the introduction. Now the second video, we handled what we call titanium, we handled vanadium, and we also handled transition chemistry involving the element of chromium. So this video is we are going to be exclusively looking at one element, which is going to be manganese as part of the transition elements. So we are going to be looking at all the reactions and all the chemistry that is under manganese together with its compounds. So we're going to start with the reactions that manganese gets involved in. So the symbol for manganese, or the chemical representation for manganese, is denoted as Mn, with a capital M together with a small n. And you're going to be starting straight out with the reactions in which manganese is going to get involved. Now, as we talked about earlier on, we said that when you're writing any reaction which has an equation, the statement must contain all the conditions that are required by the examiner to be marked to mark your work. So when you're describing a reaction for manganese to react with air, just like any other metal, it must first be heated. So the conditions here is that you must heat manganese so that it can burn in air. And after burning in air, we say that a correct statement must have conditions. After saying conditions, you must state the product which is going to be formed. Ignore the color, but you just give the product, the name of the product that must be formed. And by that, you qualify to get a mark for your statement together with a mark for the equation. But usually the statement is going to carry a half a mark if properly written. So what you're going to do is that you're going to say that manganese is going to burn in air, forming a mixture of trimanganese tetraoxide. If you look at this statement, our conditions is heating, and we also gave a product which is always formed, or which is going to be formed when manganese is burnt in sufficient air, which is going to be trimanganese tetraoxide, which is denoted by this formula. Now in the previous video, we talked about balancing equations, and we said that whenever you're balancing an equation, you start with metals followed with non-metals. So if you look here, assuming that 3 was not there, if you look at your right hand side, you're having 3 manganese atom, and the left hand side you're having 1 manganese atom. We are starting with manganese because it's the only metal present. So since we're having 3 manganese atom on the right hand side, we shall put here 3 to ensure that the metal atoms are balanced. And then lastly, we shall balance oxygen. So if you look this side, our oxygen is 4. So that's why I placed a 2 here, so that we can balance the oxygen atoms. So we're going to go to another reaction which involves reaction of manganese with water. Now manganese does not react with cold water, but when heated is going to react with steam. So the conditions here are going to be 2. 1, manganese must be heated, that is the first condition. And then the other condition is that water must be in form of steam in order for manganese to react with water. So you're going to say, first, remember that we said the first statement must contain conditions together with the product formed. So we're going to say that heated manganese reacts with steam, forming trimanganese tetraoxide and hydrogen gas. And then we form an equation for that. If you look at this statement, we have our conditions for heating manganese together with water being in terms of steam. Whenever you are dealing with any reaction involving heating and you are going to involve water, we don't write water as the name water, but instead we assume that the heating is going to cause water to become steam so that it can get into a state of reacting with the other element or compound in which we are reacting it with. So we're going to say the conditions that heated manganese reacts with steam, forming trimanganese tetraoxide together with hydrogen gas. So our statement qualifies to be marked because you have represented the conditions together with the products that are formed. And after that, we write our equation. Now, as you're balancing the equation, you follow the same procedure. Manganese atoms, there are 3 here, you have to put a 3 here. We balance oxygen as the second last. So oxygen, there are 4 here, that's why I placed a 4 on water, on the steam molecule. And then you balance hydrogen lastly. If you look this side, hydrogen became 8, that's why you placed here a 4. So let's go to the reactions that involve reaction of manganese together with both dilute and concentrated acids. Now you're going to say that manganese reacts rapidly with cold dilute hydrochloric acid together with dilute sulfuric acid. But whenever it reacts with that, it always forms corresponding manganese two salts together with hydrogen gas. Now the key takeaway from this statement is going to be that manganese is able to react with non-oxidizing acids. And the non-oxidizing acids are going to be both cold dilute hydrochloric acid together with hot concentrated hydrochloric acid, because hydrochloric acid, whether dilute or concentrated, it's a non-oxidizing acid. But sulfuric acid is only non-oxidizing when it's in dilute form or when it's cold dilute condition, when it's in the conditions where it is dilute. But when concentrated sulfuric acid is used, sulfuric acid then becomes an oxidizing agent. So whenever we react manganese with non-oxidizing acids, such as both cold dilute hydrochloric acid and hot concentrated hydrochloric acid, together with dilute sulfuric acid, we are going to form manganese two salts together with hydrogen gas. Now I told you that whenever you're presenting your statements, you make sure that you don't include the color of the compounds or products formed anywhere, unless you are asked for observation. But if you're writing equations, do not write the color anywhere. You just name the products that are going to be formed. So manganese reacts with dilute acids or non-oxidizing acids to give us manganese two salts together with hydrogen gas, and that was the required equation. Now going to the next reaction, you're going to say that manganese is going to react with cold dilute nitric acid to form manganese 2 nitrate, nitrogen monoxide together with water. Now this statement can work. Now in some books you're going to see that they didn't call it cold dilute nitric acid, but they can also call it moderately concentrated nitric acid. They mean the same thing. You can either call it halfly concentrated or moderately concentrated, or to be more chemical or scientific, you can call it cold dilute nitric acid. And when cold, remember that nitric acid is a very strong oxidizing acid. So for it, it is always oxidizing at all times. But when it is moderately concentrated or when it is cold dilute, that's why we underline this word. When it's cold dilute, it's going to oxidize manganese to give us manganese 2 nitrate, and after it oxidizing, it gets reduced to nitrogen monoxide together with water being formed. So this is a redox reaction. You should take note of that. Now I'll make a video trying to explain about the why I told you on balancing redox reactions, as I made that elaborate in the previous video. So here, manganese reacts with nitric acid to give us manganese nitrate, and the acid is later reduced to nitrogen monoxide together with water. And we say that to balance these equations properly, we use what we call redox reaction knowledge. And I told you if you have issues, try to put your issues or concerns in the comment section. Now looking at another reaction, we are going to say that manganese is oxidized by hot concentrated sulfuric acid, forming manganese 2 sulfate together with the acid getting reduced to sulfur dioxide and water. Like we say that whenever you see something oxidizing and the other thing getting reduced, that means that you are going to be dealing with redox reactions. Redox reactions can easily be recognized by having 3 products on your right hand side. So manganese is oxidized by hot concentrated sulfuric acid, giving us manganese 2 salt, which is manganese 2 sulfate, and the acid after oxidizing, it gets reduced to sulfur dioxide together with water. You make half equations by ionizing sulfuric acid, and therefore you are going to get sulfate ions together with protons together with electrons to give you sulfur dioxide and water. Now the other half equation is going to be for manganese 2 for manganese solid to be oxidized to a manganese 2 ion. And that's how you form the two half equations. Now you combine the two half equations by eliminating electrons, just like we explained under the redox reaction video. And you make sure that you be very good at balancing equations. That's the only way you are going to get good at chemistry. Make sure that equation balancing is as simple as possible on your side. Do not cram equations. Understand only the products that are going to be formed. By the balancing, you need to have good practice about it, and you need to be able to write each and every equation on your own without the help of a textbook or a teacher. Now looking at another reaction, we are going to say that manganese is being oxidized by cold concentrated nitric acid. However, also another student may say hot concentrated, because we assume that any acid concentrated is always hot. So it's oxidized by hot concentrated nitric acid for as long as it is concentrated. We form manganese 2 nitrate. Now this time around, instead of forming nitrogen monoxide like the one when you use cold dilute, when you use the concentrated one, instead of forming nitrogen monoxide like before, we form nitrogen dioxide gas together with water. Now that's the difference separating the first equation from this equation. When you use dilute, we form nitrogen monoxide, but when you use hot concentrated or cold concentrated, we form nitrogen dioxide. Also, this is a redox reaction. You form half equations for nitric acid. You ionize nitric acid. That means that it's going to be nitrate ions, protons plus electrons to give you nitrogen dioxide and water. Then you balance that half equation. You also form an equation for manganese getting oxidized to manganese 2 ion. You ignore the nitrate, and then you combine the two together, ionic equation. Now notice that the ionic equation is correct. Also the molecular equation, if at all, this is what you call the molecular equation, is also correct. So if you want to combine the ionic equation to the molecular equation, you should follow the steps that I gave in the redox reaction video. Or if you still have issues, I say that present your concerns in the comment section. Now going to another component or element in which manganese is going to react with under the reactions of manganese, we are going to be looking at chlorine. Now here still the condition is going to be heating, so that's why you're going to say that heated manganese is going to react with chlorine so as to get magnesium chloride. Like I've been emphasizing, a correct statement must contain conditions together with the products that are going to be formed. Without conditions, we assume that such a reaction is not feasible or it did not take place. For example, if a student says manganese reacts with chlorine to form magnesium chloride, that's a wrong statement, because we believe that manganese cannot react with chlorine without any specific inducement. So heating, that's why it's underlined here. Heating must be seen, because for manganese to react with chlorine, there must be conditions of heating. So heated manganese reacts with dry chlorine gas to form manganese 2 chloride. Conditions must be presented when the statement together with the products that are going to be formed. So that's why we wrote here that manganese as a solid reacts with gaseous chlorine to give us 1 mole of manganese 2 chloride, and the equation was properly balanced. Now that being said, let's look at the compounds of manganese. Now manganese, just like any other transition element, manganese exhibits variable oxidation states, and one of them is going to be the +2 oxidation state, the +3 oxidation state, the +4 oxidation states, the +6 together with the +7 oxidation states. And in the first video, when you're introducing transition elements, we gave the reasons why these elements exhibit variable transition states, and we explained everything or every property of transition elements in details. So here we are just going to be giving a hint. So we're going to say that the +2 oxidation state, the 2 4s electrons are going to be lost, leaving a half-filled 3d orbital, which is very stable. Now this is going to make the +2 oxidation state to be the most stable oxidation state out of all the oxidation states exhibited by manganese. The +2 is the most stable, that's why most of the reactions that we have formed above are in the +2 oxidation state, because manganese has variable oxidation state, but the +2 is the one which is the most stable, since the 3d orbital remains half-filled. And we say that sub-energy levels, or orbitals which are half-filled, they do not require, or they do not require, they are thermodynamically stable, hence they do not require any stabilization for them to gain stability. So since they're already stable, we assume that the oxidation state that is going to be formed when the 3d orbitals are halfly filled is going to be the most stable among the compounds exhibited or contained by manganese 2 compounds. So we're going to say that under manganese 2 compounds, we are going to start with manganese oxide. Now let's look at the various ways in which we can prepare manganese oxide. Now manganese oxide is going to be a green solid, and it's going to be obtained by heating 3 compounds. So one, we are going to heat manganese 2 hydroxide. We can also get it by heating manganese 2 carbonate. We can also get it by heating manganese 2 oxalate. And we do this in absence of air so that we can prevent further oxidation. So when you heat manganese hydroxide in absence of air, you are going to get manganese oxide together with water as the products. Now, reviewing equation balancing briefly here, we said that you start balancing with the metal atoms. So the metal atoms, manganese is 1 on the left hand side, also manganese is 1 on the right hand side. So balancing oxygen is 2 on the left hand side, also oxygen is 2 on the right hand side. And then lastly, we balance hydrogen. We're having 2 atoms on the left hand side, we're also having 2 atoms on the right hand side. Now going to manganese carbonate or manganese 2 carbonate, when you hit manganese 2 carbonate or any other group 2 carbonates, you are going to get an oxide together with a carbon dioxide gas. So balancing this, you start with the metal atoms, manganese 1, you go to the non-metals other than oxygen. So it's carbon is 1, and then lastly you balance oxygen. So you're having 3 oxygen atoms this side, you're also having a total of 3 oxygen atoms on your left-hand side. So that means that this equation is properly balanced. Now balancing the equation for oxalate, whenever you hit an oxalate, first of all, you evolve what you call carbon monoxide gas. Whenever we hit an oxalate, first of all, the gas we evolve first is carbon monoxide gas. And if you subtract carbon monoxide from this compound, you'll see that you're remaining with the carbonate, manganese 2 carbonate. So after carbon monoxide getting evolved, we remain with manganese carbonate, and decomposing manganese carbonate gives us an oxide together with carbon dioxide gas. And balancing the equation based on the principles that you have been looking at is going to be self-balanced. Now let's look at another reaction, which is going to be the property about the manganese oxide. So we're going to say that manganese oxide is a basic oxide, and dissolving it in acids, we get what we call manganese 2 salts together with water. Just like any other group 2 acid or any compound that is present in the +2 oxidation state, when react it with acids, we get respective salts that are present in the +2 oxidation state together with water. So reaction of the oxide of manganese in the +2 oxidation state with an acid is going to give us a manganese 2 salt, which is going to depend on the anion present on the acid together with water as the only compounds that are going to be formed. Balancing, you follow the same steps just like we described earlier above. Now looking at the other compounds in which you can look, or in which manganese exhibits the +2 oxidation state, we are going to look at the manganese 2 hydroxide. Now just a brief talk about the manganese 2 hydroxide. This is going to be a white precipitate. Now usually you're going to see this in the laboratory under your practicals. So it's a white precipitate. It's obtained as a white precipitate when we add sodium hydroxide or ammonia solution to a test solution of a manganese 2 salt, or a test solution containing manganese 2 ion. So what happens is that, just like you do in your practicals, the manganese ions that are present in the test solution react with hydroxide ions that are coming from either sodium hydroxide or ammonium hydroxide or ammonium solution, forming manganese 2 hydroxide. Balancing the equation, you follow the same procedures. So looking at that, we are going to say that this white precipitate of manganese 2 hydroxide always turns brown after a very small period of time. And this is because due to area oxidation. When I say area oxidation, I'm meaning that oxidation by oxygen that is coming from the air in order to form anhydrated manganese 4 oxide. So usually we form this one as a dark brown precipitate in the laboratory. Immediately after addition of the sodium hydroxide or ammonia solution, you observe white precipitate. By this white precipitate, gradually within few minutes or not even seconds, is going to turn dirty brown. And it turns dirty brown due to oxidation of manganese 2 hydroxide to a more stable compound, which is going to be hydrated manganese 4 oxide. Now, hydrated manganese 4 oxide is written in two formats. In this video, I decided to pick one, as many equations confuse learners when you present transition elements. So I try to minimize the equations to the most relevant, but understand that there is another equation of manganese for hydrated manganese 4 hydroxide, but this is one of the most commonly used. So manganese 4 hydroxide gets oxidized by the oxygen present in air from the atmosphere to give us hydrated manganese 4 oxide. Balancing the equation, we follow the same steps. Now you are going to note that hydrated manganese 4 oxide is brown, but the one which is anhydrous is going to be black in color. Now we usually get the one which is anhydrous by heating a nitrate of manganese, and this is going to be a very common question under all the questions that you see manganese in. So you should underline it and you mark it down. Also, mocks like to examine this compound. How do you get manganese 4 oxide, which is black in color? They may just describe it by color, and they tell you that a compound was heated of manganese to get a black compound. Or it's not that we get manganese 4 oxide after heating manganese to nitrate. That's how we prepare manganese 4 oxide. Manganese 4 oxide, when it's anhydrous, is going to be black in color. But manganese 4 oxide, when it is hydrated, is always a dirty brown precipitate, or simply a student can say it's going to be a brown precipitate, based on what your practicals are going to be giving you. Now let's look at the salts that involve the manganese 2 ion. So you're going to say that most of the manganese 2 salts are going to be pink in color, and manganese 2 carbonate is going to be red. Now you're going to say that, or to add that, manganese 2 chloride crystals, which are written by this formula, hydrated manganese 2 chloride, can be obtained by heating manganese 4 oxide together with concentrated hydrochloric acid, and we are going to obtain them as pink crystals at the bottom of our test tube or boiling tube. And the equation for that is, remember that this equation is the same equation that you studied at O level as a substitute that you can use for preparation of chlorine gas if at all you don't use potassium permanganate. Also, this equation is a redox reaction. How did I see that it's a redox reaction? I'm having three products on my right hand side, and I told you that whenever you're having three products on your right hand side, most of the times that's a redox reaction. So what you should note is that here manganese 4 oxide is getting reduced to manganese 2 chloride. So the reduction of equation is going to be for manganese 2 oxide as a solid getting reduced to manganese 2 ion together with, so when you're writing the reducing equation, so here manganese 4 oxide is going to be the oxidizing agent. Remember that the oxidizing agents always have the protons together with the electrons on the right hand side. So if you're writing manganese 4 oxide, if you're making the half equations to so you can balance this one properly, you write manganese 4 oxide, you also add protons, you also add electrons, and it's going to be reduced to, after oxidizing, it gets reduced to manganese 2 ion. So you write manganese 2 ion together with water, and then you balance that equation. Now the one which was being oxidized was the hydrochloric acid, but here we don't take the whole acid. We ionize the acid, and we are going to just take chlorine. So since it's the major ion, so we are going to say that the chloride ion in hydrochloric acid was oxidized to chlorine gas together with plus electrons. And then you balance the two half equations, then you add them according to the redox reaction knowledge. which you already covered, and then you see how you can properly balance that equation. I'm overemphasizing balancing of equations because equations is what makes majority of you to run away from transition chemistry questions, which must not be the case if you're a student who is studying from this channel. Now proceeding, we are going to be looking at manganese 2 sulfate crystals, which are denoted as hydrated manganese 2 sulfate. And you're going to say that these ones are going to be obtained simply by heating manganese 4 hydroxide or manganese 4 oxide together with concentrated sulfuric acid. So when you're heating manganese 4 oxide together with concentrated sulfuric acid, we expect you to get manganese 2 sulfate together with oxygen and water as the first component. Now the pink crystals form from the solution that is going to be present on cooling. When you're writing this initially, you're going to have manganese 2 sulfate together with oxygen being evolved and water. But when you allow the reaction to cool, you're going to be forming your pink crystals together as the solution is cooling. Now let's look at also manganese 2 nitrate or preparation of manganese 2 nitrate. So we're going to be preparing manganese 2 nitrate simply by reacting dilute nitric acid and manganese 2 carbonate followed by crystallization. So when you get manganese 2 carbonate, you react it with a nitric acid. Now usually you're going to do this in practicals, whereby you get your salt, the mixed solid Y, they tell you to add nitric acid, dilute nitric acid. Usually you see effervescence of a colorless gas, which is always going to be carbon dioxide, together with a salt that is going to be formed after addition of that acid. So the salt which is going to be formed, we get the anion which is present on the acid, and you also get the cation which is present on the compound, so that you can get the manganese 2 nitrate. Most of the compounds that you are forming are in the plus oxidation state, because we say that the most stable oxidation state of manganese is the +2, because the 3D subenergy level is halfly filled when the 4s electrons are being lost. So that means that the +2 out of the 5 oxidation state, or the 6, is going to be the most stable. So when you react manganese 2 carbonate together with dilute nitric acid, you're going to form manganese 2 nitrate, carbon dioxide gas together with water. Balancing is going to follow the same procedure. Now here we are going to also look at manganese 2 carbonate to be obtained by the reaction that you can call precipitation. So you're going to say that manganese 2 carbonate can be obtained by simply adding sodium hydrogen carbonate to a solution containing manganese 2 salt. So when you're having sodium hydrogen carbonate, what you're interested in is going to be the hydrogen carbonate ion, and then you react it with a solution, e.t.c solution containing manganese 2 ions to get you the manganese carbonate, carbon dioxide together with water, just like previously above. Now this is a precipitation reaction since manganese 2 carbonate is a precipitate. Now we say that manganese 2 carbonate is red in color as we are starting the reactions about manganese, or the manganese 2 compounds. Now let's look at the manganese 3 compounds, or compounds of manganese that are present in the +3 oxidation states. So we're going to say that compounds of manganese in these states are going to be uncommon simply because of the disproportionation reaction that they exhibit. Now let me talk about disproportionation reaction. A disproportionation reaction is going to be that reaction in which the same species undergoes both oxidation and reduction simultaneously. So if you look here, if you look at this equation that we gave as an example down here, manganese currently is in the +3 oxidation state. But if you look at the product side, one of the products we have got, manganese has went to the +2 oxidation state. That means that the same species has been reduced. But also we have formed another product of manganese, but here we have formed manganese 4 oxide. So here manganese in the present in the +4 oxidation state. So that means that manganese 3 ion, as we started with in the reactant, has been reduced at the same time as being oxidized, and that's what we call a disproportionation reaction, which is going to be that reaction in which the same species undergoes both oxidation and reduction simultaneously. Like the example I gave here is well elaborative. Manganese is present in the +3 oxidation state, and here is present in the +2. That means that it has been reduced. And here it is present in the +4 oxidation state. That means that it has been oxidized, which have all occurred in the same equation. So whenever you are defining a disproportionation reaction or you are taking notes, you make sure that you note it aside that a disproportionation reaction is going to be that reaction in which a similar chemical species undergoes both oxidation together with reduction. Now, after looking at compounds of manganese, we said that they are going to be uncommon. That's why we didn't talk about or give sufficient information about them, because also the questions under it are going to be most quietly or unquietly seen under the examination boards. So let's look at the manganese 4 compounds, which is the most or second stable oxidation state of manganese. So if you look at the manganese 4 compounds, the major one is going to be manganese 4 oxide, and I say that this one is most likely by examination bodies in terms of asking how it is prepared. So that's why I started with that as my main emphasis as I was writing down these notes. So I say that anhydrous manganese 4 oxide is a black solid which is going to be prepared by heating manganese to nitrate, just like I already mentioned. So when you're having manganese to nitrate, you heat it, you're going to form manganese 4 oxide, which is a black solid. We say that it's a black solid when it is anhydrous, and it's a brown solid when it is hydrated. When you heat manganese to nitrate, unlike other nitrates, you form manganese oxide together with nitrogen dioxide gas. This equation is very common. Whenever you are revising manganese, make sure that you put a star on it and you don't forget it because it has a more likely chance of surfacing whenever we examine questions about manganese as a transition element. So when you heat manganese to nitrate, you're going to form manganese oxide together with nitrogen dioxide gas. Balancing, you follow the same procedure. You start with the metal, which is manganese, you go to the nitrogen, and then lastly, you balance the oxygen, and the equation will be balanced. That's how we simply balance equations. I say that the main benefit you should take away from this channel is mastering chemistry. So let's look at also the oxidation of manganese to salts. And also, so we're going to say that by oxidation of manganese to salts using sodium hypochlorite and sodium hydroxide solution, we are going to form manganese oxide. So when you're having sodium hypochlorite together with mixed with sodium hydroxide as the alkaline medium, and we get a test solution which is containing manganese to iron, we are going to form manganese oxide. But remember that here, manganese oxide is going to be in solution. That means that it's going to be hydrated. So since it's hydrated, it's going to appear as a brown precipitate. But here, when it's anhydrous, it appears as a black solid. So if for manganese oxide, it's a solid, but it's seen as a precipitate, which is going to be brown in color. And then after the hypochlorite oxidizing, it gets reduced to the chloride ion together with water from the sodium hydroxide. Now we're going to add that manganese oxide is essentially ionic, in that you're going to say that it is going to dissolve in cold concentrated hydrochloric acid to form hexachloromanganate 4 as a complex. So when you're having manganese oxide, you add it to cold concentrated hydrochloric acid. This statement is very important. Cold concentrated, because hot concentrated, if you use hot concentrated, remember that is going to be preparation for chlorine gas. But however, when you use cold concentrated, you must underline this word and you must pay attention to it properly. That's why I only presented the chemistry of manganese in this video, because there is a lot of information that is packed behind these elements. So when you're using cold concentrated hydrochloric acid, you are going to form hexachloromanganate 4 as a complex together with water accompanying the reaction. So what we do is that we ionize the acid, since we are interested in the ions present in the hydrochloric acid. We don't take hydrochloric acid as a whole. We only take it as a whole when you're dealing with hot concentrated hydrochloric acid, which I'm going to talk about in a second. So when you're having manganese oxide, you ionize the cold concentrated hydrochloric acid, you're going to form a complex of hexachloromanganate 4 complex. I hope that you are very good at naming complexes, because we looked at that under the introduction video, which was video number 1, about transition elements. Together with water balancing, we are going to follow the same criteria. So, but when manganese oxide reacts with hot concentrated, remember that the first statement was about cold concentrated. When reacted with cold concentrated, that's when you form a complex. But when you react it with hot concentrated, we do not form a complex. But instead, this is a redox reaction involving preparation of chlorine gas. So when you react manganese oxide together with hot concentrated hydrochloric acid, manganese oxide oxidizes this hot concentrated hydrochloric acid to give us the chlorine gas. I said that this reaction was covered in O level as an alternative for potassium permanganate. So this is a redox reaction. You make half equations, as I said earlier. Manganese oxide is going to be reduced to manganese to iron, and then hydrochloric acid is going to be oxidized to chlorine gas, as presented in this equation. You balance the two half equations and you get the ionic equation, and then it's how you can balance the molecular equation. But also, the ionic equation is fully marked. Now, looking at another reaction, you're going to look at the reaction of manganese oxide together with hot concentrated sulfuric acid. Now, both of these ones, both hot concentrated sulfuric acid and manganese oxide, are both strong oxidizing agents. So what happens is that the reaction just takes place, both oxidize each other, but here you find that manganese is going to have the most power. So manganese is going to oxidize hot concentrated sulfuric acid. After oxidizing it, it gets reduced to manganese to sulfate. So this manganese in this compound is containing the oxidation state of +4. After oxidizing, it forms the compound of manganese to sulfate, in which its oxidation state is now +2. Now it's going to oxidize the sulfuric acid to get oxygen gas together with water. And the balancing for this equation is not quite mathematical, but if you follow the steps that we look at when you're balancing equations, you're going to get it correct. We say that you start with metals, you go to non-metals other than oxygen and hydrogen, then you balance oxygen, and then later you balance hydrogen. But when you're balancing these atoms, make sure that you leave oxygen untouched as you are balancing your equation. Oxygen molecule as a gas should be untouched. That's always what you should put in your head, or what you should memorize. So proceeding, we are going to say that manganese oxide oxidizes oxalates to carbon dioxide in presence of an acidic medium. So if you're having manganese oxide, since it's a strong oxidizing agent, or it has oxidizing properties, it's going to oxidize the oxalate ion in presence of an acidic medium to give you the manganese to iron carbon dioxide gas together with water. Now this is a redox reaction, and I think we looked at this one under the redox reaction video. So the first half equation is going to be oxalate present in acidic medium plus protons to get reduced to carbon dioxide and water. Now the other half equation is going to be manganese oxide plus protons plus electrons, and they are going to give you a product of manganese to ions plus water. And then you balance the two half equations by eliminating electrons, and then you see the equation you end up with. Now let's look at the theory or the practical applications of manganese oxide. Now you're going to say that during determination of the percentage of manganese oxide present in any compound or any substance that you're going to be provided with, for example in the laboratory, the soils that they give you. First of all, we get a known mass of the ore, which is also known as the pyroxite, and is dissolved in hot concentrated hydrochloric acid. After that, we get manganese oxide. Manganese oxide, which is present in that ore, is going to dissolve or react with the hydrochloric acid in which it has been dissolved to give us or to liberate the chlorine gas. Now remember that it's liberating the chlorine gas because we are using hydrated concentrated hydrochloric acid in its hot format. But if it was dilute, I said that you form a complex. Always remember that. So manganese oxide reacts with hot concentrated hydrochloric acid and it gets reduced to manganese chloride, and the hydrochloric acid is oxidized to give us chlorine, and then water is also formed as after reducing manganese oxide to manganese chloride. So what you're going to say that now this is also a redox reaction. Just because we are repeating these equations, that's why I'm not overemphasizing them. So looking at chlorine, you are going to say that the chlorine is going to be liberated. The chlorine which is liberated is going to be bubbled through excess potassium iodide solution to liberate iodine. Now we looked at this reaction in details under chemical equilibria, which is also a video which is already uploaded on this channel under the playlist of physical chemistry. So what happens is, since chlorine is an oxidizing gas, when you bubble it in a solution of potassium iodide, the iodide ions that are coming from potassium iodide are going to be oxidized by this chlorine, since it's an oxidizing agent. So chlorine oxidizes the iodide ions from potassium iodide to give us the iodine, and after it oxidizing, it gets reduced to the chloride ions. And that's the general equation for that. This equation is very common under questions that involve chemical equilibria, especially in your mock examinations. So that's why it's very important, and that's why I had to bring it in this platform to be viewed as in general. Now look at another step. You're going to say that a known volume of the solution containing the liberated iodine is going to be titrated with a standard solution of sodium thiosulfate. And whenever you use a standard solution of sodium thiosulfate, always we use touch as an indicator. So you're going to write an equation for iodine reacting with sodium thiosulfate, and after these two reacting, just like we looked at it under physical equilibria together with chemical equilibria. In fact, all the equilibrias, physical, ionic, and chemical. After iodine reacting with thiosulfate, you form a complex together with the iodide ion after iodine oxidizing the thiosulfate ion. So for us to get the mass of manganese oxide present in that ore is going to be calculated, and the percentage of the ore is going to be obtained by the following method. So for us to obtain the percentage of manganese oxide, you get the mass of manganese oxide present in the ore divided by the ore mass of the ore which has been presented. And that's a background theory about the practical application of manganese oxide. Now let's look at the other compounds of manganese, which are going to be the compounds of manganese present in the +6 oxidation state. Now you're going to start with sodium and potassium manganate 6, or sodium and potassium manganate manganate 6 to be, I think this was a mistake. This was supposed to be manganate 6, not manganese 4. So make sure that you edit that as you're taking your notes. So sodium and potassium manganate 6 are going to be dark green crystals, and they're going to say that potassium manganate 6 can be obtained by fusing potassium hydroxide together with manganese oxide, but this is going to be done in presence of excess oxygen. Now this is a very important reaction about manganese. Like I said, there are very many equations, but I tried to minimize and be concise when I was bringing this topic in front of you to reduce the confusion that is got by majority of the students. So one key takeaway you should take is that you need to understand each and every compound under each and every oxidation state of manganese, because it's very, very important. Understand their colors. So you say that the compounds of manganese that are present in the +6 oxidation state are going to be dark green crystals. This is something that you should highlight in your notes, because that's how mocks are going to present your examinations. And after that, we have said that for us to obtain potassium manganate 6, or for these dark green crystals to be prepared, we get what we call our alkali, which is going to be potassium hydroxide, and then we fuse it with manganese oxide. But this is done in presence of excess oxygen to allow the reaction to take place without hesitation. So manganese oxide is reacted with potassium hydroxide in presence of air or oxygen to give us green crystals of potassium manganate 6 together with water being formed. Now this is a solid. Note that it's a solid. If you have been good at revising and you look at majority of the mock bodies, we said this reaction often because it confuses students. First of all, when you're writing initially, is that you will see dark green crystals being formed. But after these crystals being formed, they dissolved in this water, which is formed to give us an aqueous solution of potassium manganate 6. So initially, it's going to be a solid. That's why when you're setting, we describe it as a solid. But later in the question, we tell you that it's going to become an aqueous solution, and we tell you to react that aqueous solution with other compounds or elements as it will be dictated by the question. But you should understand that we first form crystals, but these crystals later dissolve in this water which is being formed here to give us an aqueous solution. So a solid can easily be written as aqueous. But initially, when you're writing this equation, you make sure that you write it as a solid because we form it as a dark green crystal. But remember that crystals are easily soluble in polar solvents, such as water. So we're going to say that the manganese 6 ion is only stable in the alkaline medium. So what does it mean? If you put it in an acidic medium or a neutral medium, it's going to undergo disproportionation. Remember what I told you about disproportionation? A reaction in which the similar species undergoes both oxidation and reduction. So let's look at the equation to elaborate that. So you're going to have both equations when manganese 6 ion is placed in an acidic medium. You have said that it's only stable in the alkaline medium, and if you put it in any other medium, it's going to undergo disproportionation. But for all these disproportionations that we form the same ions. One, we form the manganese 7 ion because the manganese 7 ion is the most stable in acidic medium, and then we form the manganese 4 oxide solid together with water. We form water when you put it in an acidic medium, but when you put it in a neutral medium, instead of water, we are going to form the hydroxide ion. So it's manganese 6 ion undergoes disproportionation in that here it's forming the manganese 7 ion. So that means that here it's going to be oxidized, and here it's forming the manganese 4 oxide. So that means that here it's going to be reduced, and that's why the two equations are being called disproportionation equations. Now proceeding, you're going to say that even bubbling carbon dioxide gas through a solution of manganese 6 ions causes color change to dark green, from green to purple with formation of a black solid. Remember that the one which is purple is going to be called manganese 7, which is this one, and the black solid is going to be manganese 4 oxide. Now we say that it's black when it's anhydrous, but since we're having a solution, we are going to say that also students who say that it's going to be brown solid is going to be marked. In fact, that will be the most correct statement. So when you're having your manganese 7 ion in a test solution, and then you bubble carbon dioxide gas, remember that this is green in color. So the observation is going to be green solution slowly fades into a purple solution with formation of brown or black solids. Now you don't say deposit, you do not have deposit in chemistry. You leave that in your general life or to business subjects. We do not have deposits in history. You say formation of a specific solid or a precipitate. So dissociation occurs when you bubble carbon dioxide through a solution containing manganese 6 ions, and you form a purple solution due to formation of manganese 7 ions, and a black solid or a brown solid due to formation of manganese 4 solid together with the carbonate ions. And then you balance the equation based on the principles that you have earlier on discussed. Now let's look at the compounds of manganese 7 ion. Now here we are going to start with potassium manganese 7. Now let's first look at its properties or its physical properties or the favor, because you use this one mostly in practicals. Now let's first give a brief history or a brief introduction about it. Now first of all, any compound of manganese 7 is going to be purple in color. So potassium manganese 7 or permanganate is a dark green crystalline compound which is going to be soluble in water, forming a purple solution. The purple color is because the manganese ion is present in the +7 oxidation state. So you're going to say that it's going to be used in the laboratory for preparation of chlorine gas and testing for the presence of sulfur dioxide together with unsaturated hydrocarbons, because it's mostly used in organic analysis and practicals. Now it's used in volumetric analysis and organic chemistry as an oxidizing agent, which I've already talked about earlier on. So proceeding, we are going to say that it's going to be used in neutral alkaline together with acidic medium. Only sulfuric acid is going to be used when we are acidifying potassium manganate 7. And the reason for that is because nitric acid is not used because it's a strong oxidizing agent. So both of them, since nitric acid is a strong oxidizing agent and potassium manganate 7 is also a strong oxidizing agent, both of them are going to compete during chemical reactions. So that's why we only use sulfuric acid to oxidize potassium permanganate. Now you may ask, what about hydrochloric acid? Hydrochloric acid is not used simply because it is going to be easily oxidized to chlorine. Like I told you, when you're preparing chlorine in O-level, you used to get potassium permanganate and then you add it to hydrochloric acid. So that reaction, we don't use hydrochloric acid because, and this is a very common question in mock bodies, we do not use hydrochloric acid simply because hydrochloric acid is easily oxidized to chlorine gas. So the equation is a redox equation because you're having 3 reactants together with 3 products. And we have already talked about how redox equations are balanced. So I'm not going to waste time there. Now let's look at the advantages. Like I said, these are mainly examined by examination bodies. That's why I emphasized them and I brought them in this compartment. So I'm going to say that advantages of using potassium permanganate in volumetric analysis are going to include the following. One of them is that potassium permanganate is a self-indicator. Remember that in practicals, you can easily see that the purple solution is turning colorless. That's what we mean by saying that potassium permanganate is a self-indicator. Now the other thing is going to be that potassium permanganate is having a high relative molecular mass or a high formula mass, which is going to minimize weighing errors in the laboratory. When you're preparing Fa2 or Fa1, Fa1 is usually an acid, but when you're preparing Fa2, we always weigh the amount to be used in preparation of such solutions. Now, due to the high formula mass or the molar mass of potassium permanganate, it minimizes weighing errors when you are making those solutions. Now, the other advantage is potassium permanganate is highly soluble in water, and therefore, when you're making such solutions, Fa2, it doesn't give us hard time when you're preparing them. The other thing is going to be that most of its reactions occur fast enough at room temperature. That's why majority of the laboratories you care about number one volumetric analysis, they do not involve heating, except a few which involve heating, but usually they do not involve usage of potassium permanganate. So looking at why potassium permanganate is not used as a primary reagent. So one of them is going to be that it's always found contaminated with manganese 4 oxide. Like we say that manganese 2 ions always undergo disproportionation reactions, and whenever they disproportionate, they form this solid of manganese 4 oxide. So usually when you leave them in the laboratory open, you form those solids or precipitates present in that solution. So it's not quite advised. Remember that every advantage, everything or every reagent has an upside and a downside. So one of its downside is always contaminated with this compound of manganese 4 oxide. Now proceeding, we are going to say that also the other downside is that it's not highly stable, in that in presence of light, the solution of potassium manganate 7 is always decomposing, forming manganese 4 oxide, which I've already explained. So manganese unacidified acidified potassium manganate 7 in presence of light, a solid is decomposing to form a brown solid in solution of manganese 4 oxide. Remember that we say that when it's anhydrous, it's black in color, together with formation of water and oxygen gas. That is done in presence of light. But in presence of alkaline medium, because remember that I say that manganese 7 is only stable in acidic medium in absence of light. But if you put it in another medium, we say that it's only manganese 6 which is stable in the alkaline medium. So when you put it in a medium in which it is not stable, we form an oxidation state of magnesium or an ion of manganese which is stable in this medium, and that is manganese 6. So that means that our purple solution is going to slowly fade to another compound. Now here, this is present in the neutral medium because water is neutral. But when you place it in an alkaline medium, I think I forgot to write the equation. When you place it in alkaline medium, you're going to form a manganese 6 ion. So that means that your purple solution will be turning into a green solution. Like I've told you, make sure that you use these notes appropriately. View as many mock papers as possible to see how these questions are set, so that you can get good results in your trials and the mock examinations that are coming your way. So manganese, the general equation, when you place it in an alkaline medium, it's also going to decompose, forming brown solids of hydrated manganese 4 oxide. Manganese 4 oxide, when it's anhydrous, is black, but when it's hydrated, it's brown in color, together with hydroxide and oxygen gas. Now, the other oxidizing properties of the manganese 7 ions that you are going to look at are going to include the following. So in neutral medium, oscillate alkaline manganese is going to be reduced to manganese 4 oxide, which I've already talked about earlier on above here. Now, for example, if you get this equation and then you combine it with the iodide ion from the iodide is going to react with the hydroxide ion that is formed after manganese 7 decomposing to give us the iodate together with the water. Now, the two alpha equations are going to be balanced simply by eliminating these electrons, just like redox reactions, and the overall equation is going to be the following. But this one is commonly evidenced in chemical equilibria. You look at it more in details under chemical equilibria. It may not be quite necessary under inorganic chemistry. That's why I'm not going to give it enough attention in explaining it. So we say that in strong alkaline medium, the manganese 7 ion is going to be reduced to green manganese 6 ion, because I've told you that in alkaline medium, it's only manganese 6 ion which is stable. So if you put the manganese 7 in alkaline medium, we always form the most stable ion, which is the manganese 6. So the observation there is going to be that the purple solution of manganese 2 ion turns to a green solution containing the manganese 6 ions, because they are the only ones stable in the alkaline medium. So if you go to the stronger acidic medium, the manganese 7 ion is going to be reduced to manganese 2 ion. Unless stated, the solution is going to turn from purple to colorless, and you're going to look at this as evident under organic analysis. So when you're doing your practicals, you make sure that your teacher shows you this specific reaction, because it must be seen. And this is a redox half equation, which already described on earlier. Now let's look at some of the specific reactions or the redox reactions that involve manganese 7 ion. Now here, since I've already explained the redox video in separate, I'm just going to be going through them. So oxidation of manganese 7 has the ability to oxidize nitrates to nitrates. So the equation or the overall redox equation is going to be the following. To balance these equations, you follow the principles that I've already explained earlier on. So to save some time, I'll just let you pause the video and you take down these notes about the redox equations, because we already covered them under the topic of redox reactions. So you pause the video and then you take notes about these reactions. So similarly, also these ones are redox reactions. What you should note here are the observations. When we ask you for observation, only state the color changes. Do not name Do not give the name of the product in your answer. Observations must strictly contain colors: colorless, purple, green, colorless, purple, green, yellow. Deposit, I've said eliminate it. Let's use either solid or precipitate. We do not have deposits in chemistry. So you take down the notes. What you should note, I've said that I'm emphasizing this, when you're stating observations, only state the color changes. Don't give the name of the product. You only give the name of the product when you're going to write an equation and you're making a statement for it. That's only we give names of products. But when you're giving observations, we want you to examine what you're seeing. And you can't tell us that you're going to be seeing the name of the product. You're only seeing color changes. That's what you should present to the examiner as required, or as the question requirement. Now let's go through the qualitative analysis of manganese 2 ions as quickly as possible. So we're going to start with the qualitative analysis of the manganese 2 ion. Now in sodium carbonate, just like we looked at the other ones, they are going to have quite similar properties. So we are going to say that a brown precipitate which rapidly turns brown is formed. Hope you notice how I'm giving my observations. I am not stating any name of a compound anywhere, but I'm just giving color changes and textures of the compounds that are going to be formed. So a simple explanation for this, just as a reminder, is that the brown precipitate is due to oxidation of our white precipitate of manganese trihydroxide to hydrated manganese 4 oxide as a result of aerial or atmospheric oxidation. And the first equation is going to be formation of the white precipitate, which is going to be that of manganese hydroxide. But this white precipitate, within a few seconds, is oxidized by oxygen from the atmosphere to form hydrated manganese 4 oxide. Now the other reagent that you're going to look at is ammonia solution. So observations simply also going to be brown precipitate that rapidly turns brown on standing, and the equations are going to remain the same way like the one for sodium carbonate, and the explanation is going to remain the same. So since the equations are going to be remaining the same, let's talk about the observations only. When you're reacting with the ammonia solution, this was a repetition. Brown precipitate rapidly turns brown on standing, and you're going to form these equations. The other reagent is going to be, now this is the most commonly required reagent, because this one is one which conforms the manganese ion. There are two major reactions that conform manganese to iron, so you should know them properly and the arrangement of the reagents. So first of all, you get a solution, then you add concentrated nitric acid followed by solid sodium bismuth. And the observation is that it must only contain color changes together with the textures that are going to be formed. So there the color changes is going to be purple solution turning to, your observation according to the test solution, you might have a colorless solution turning to a purple solution due to oxidation of manganese 2 ions to manganese 7 ion. Remember that manganese 7 ion is a purple solution, and I've said that this is a very common question because it's a confirmatory test about manganese ion. So if you're taking notes, you put a sterific note on it. And let's look at the equation. The equation is specifically a redox reaction. So for you not to forget, we say that here, in such a type of reaction, manganese 2 ions are oxidized to manganese 7 ions, and that's why we form a purple solution by bismuthate. So that means that bismuthate here is going to be the oxidizing agent. So when you're forming your half equations, the first half equation is going to be this one: bismuthate plus protons plus. Now we saw that we said that solid bismuthate, but here we're writing aqueous. We're writing aqueous because when you put it in solution, it dissolves. So write it as aqueous. So sodium bismuthate, when you're writing your equations, you write bismuthate plus protons plus electrons, and it's going to get reduced to bismuthate ion plus water. And the other equation is going to be manganese 2 ion plus water to be oxidized to manganese 7 ion, and then plus proton plus electrons. Now you combine the two equations by eliminating electrons to end up with this general equation that you're seeing in front of you. And you make sure that you must be successful in balancing such an equation. Now looking at the last reaction, we are going to look at the reaction involving concentrated nitric acid reacting with solid lead 4 oxide together with warming in place. So the first observation that we are going to observe is that our purple solution is going to be formed. Now these two, either the number 3, which is this one, or this one, are the only confirmatory tests of manganese iron. So you make sure that you master the two, because examination bodies will bring them, two of them compiled. We either bring one or we bring both. There's no way you can survive any in case we set a question about manganese. So the observation is going to be purple solution being formed. Now usually it's due to oxidation of manganese 2 ions to manganese 7 ions by lead oxide. So arrangement of reagents is going to be very important. One is going to be concentrated nitric acid, you follow it with solid lead oxide, and then you warm. So the equation is also going to be a redox reaction. Lead oxide plus protons plus electrons to get reduced to, now change this to lead 2 ion, to get reduced to lead 2 ions. Now it's bismuth plus water, and the other equation is going to be oxidizing manganese 2 ions plus water plus water to give you manganese 7 ion plus protons plus electrons. You add the two equations to end up with this general equation, and that's how you balance the redox reactions. I say that these reactions are not complicated. Do not crown the coefficients. Understand how they come about. Understand or master how to balance equations. That's how you are going to enjoy the gift of knowing chemistry. Now this brings us to the end of this video. Success in your academic journey. We'll meet in the next video. Now the next video is going to be introducing iron as another transition element. So you're going to be remaining with basically two videos, which is going to total up to a sum of 6 videos. Now share the video to your friends and make sure that you all benefit as a group. See you in the next video.